Okay, so I've started the recording. We're gonna finish up chapter one and start chapter two. The quote of the day today, which is a little bit off of the screen here. Let me move this window a bit. Um, Again, sometimes it's a quote, sometimes it's just more of a general idea. Um, but the kind of idea today is to make strategic use of the learning curve. So you might have heard of this idea of the learning curve, that sometimes things are kind of a little bit difficult to learn at the beginning and then they become easier. But I think there's kind of a similarly shaped learning curve where if we say kind of on the horizontal axis, if we look at the amount of knowledge, the amount you know about a certain topic or field versus the value, either something like the economic value or just the value to your life, I think we see kind of a similar curve. So this is the learning curve I like to think of. I think this is the kind of optimistic view of the learning curve. So in other words, if I put in a little bit of time and effort to gain, a moderate amount of knowledge about, say, a certain topic or about a certain field, that kind of has an outsized value relative to the time and effort that I put in. If I want to become the top expert in the country in a certain field, I pretty much need to devote my entire life and all of my time to that specific field and really not be good at pretty much anything else. But if I can kind of be a jack of all trades, if I can, devote some time here to this topic and get reasonably proficient at that, and then devote some time to another topic, get reasonably proficient at that one, I bring a lot more components of value to the table, to a future employer, to a piece of coursework, or just kind of to general life and how I view the world. Um, and then the other thing is that gives me a nice broad foundation to build off of. Again, with this idea of general education, why do we want a broad foundation instead of very narrow pieces of expertise? Because we have more to build off of. If if I'm interested in kind of business or finance in general, but then maybe there's a job or a promotion that comes up where I need to be a little better at, say, data analysis. Well, if I know a little bit of programming already, if I've taken a couple of stats classes already, if I have, accumulated this much knowledge, it's going to be easier to accumulate the next little bit of knowledge that I might need to get to make that promotion work, or to perform better in a job that I might want. Kind of a related idea, and this is kind of my idea, so you can, take it with a big grain of salt if you want. I like to divide knowledge into kind of four quadrants. So two criteria, we can have, two selections for each of them. And one is what I call the time constant. Kind of an important idea across mathematics, but in this sense, it's kind of like if I take the effort to learn a piece of knowledge, how quickly does its value go to zero? Right. So slow time constant means that piece of knowledge kind of stays valuable and relevant for a very long time, versus fast, meaning it goes to zero pretty quickly. So for instance, if you're in IT, say tech support, you need to constantly keep updating your knowledge bank, because what you knew about, whatever, this version of Windows or that version of Microsoft Word, well, they come out with a new edition and that changed. So now you need to update that, right? That you spent some time learning something, and then when the edition updates, that time, that time and that knowledge devalues very quickly. You need to learn something else. And then also the nature. It's so we could have something like foundational knowledge versus trivial knowledge. In other words, if I learn a piece of knowledge, does it help me learn other pieces of knowledge more easily or more quickly? So I like this quadrant, things with slow time constants, where if I learn something, it stays relevant for a long time, and where it's foundational, where if I learn something, it helps me to learn other things. And maybe my bias is there because math kind of fits these two categories. If I learn a mathematical theorem, or an idea in statistics, I can build off of that with other ideas. And if I learn some theorem, it's effectively never going to change. I don't like personally this quadrant so much. I try to stay, that's not to say I should never learn anything in that quadrant, but I try to stay out of that quadrant. You know, the stereotypical example in this quadrant is something like sports, right? You watched the game yesterday and you say, oh, there was this really cool play, and you can talk around the water cooler with your buddies about it, but a week or two from now, nobody really is interested in talking about that anymore. That kind of value has gone to zero. And also, it's kind of trivial. If I know something about this play, that doesn't really help me to understand something greater about the world or about football, at least most of the time. Another example of this is kind of politics, right? Oh, did you hear what this politician said or something like that? Well, nobody really cares about that in a couple of weeks. And again, it's fairly trivial. It's like, well, can you really build something foundational off of that? And, you know, these quadrants where you have a trivial piece of information, but slow time constant, maybe something like learning somebody's name, right? That's kind of intermediate for me anyway. Or fast time constant might go to zero, but it's a little more foundational. I think these are a little harder to tease out, but this might be something like, say, learning a programming language, right? If I learn, you know, something about Python, maybe that's not the hot language in 5 years. That, you know, knowledge, that expertise can devalue maybe somewhat quickly, but it is foundational. If I learn a programming language, I can really build upon that and build upon those ideas to do other things well too. So anyway, that's kind of my thought with this. I would prefer to be something more like a jack of all trades than to be an expert in one. And then if that, you know, if you're the expert VCR repairman and DVD players come out, you're in a tough situation. And I would prefer information or knowledge that is going to last a long time and that I can build off of. So, and again, I'm not saying, you know, never watch sports or never watch politics, but I'm just saying, you know, if you have to make a choice, maybe bias your time one direction or another. Okay. So moving over now to the last little bit in chapter 1. And I'm actually going to pull this screen. Oh, I'm going to pull this screen over a little bit so that I can just kind of work right off of this. We have several examples of bias here. And if you remember from last time, we said that we call a statistic something that's computed based on a sample from a population. We call it biased if it's computed in a way that's systematically different from its population parameter. So remember the fundamental idea that we talked about in chapter 1, and a very important idea across all of statistics, is we have a population, the group that we want to say something about, but typically we can't evaluate the population directly. Typically it's too large, it's infeasible for us to evaluate the whole population directly. We're stuck taking a sample that's much smaller than the population and evaluating the sample. I typically would like to know a population parameter, maybe like the average height of people in Pittsburgh, and I'm stuck with a sample statistic, maybe the average height of this random sample of 100 people from Pittsburgh. And the question is, when I compute that sample statistic, what I would really like to be true is that sample statistic is kind of like on average equal to the population parameter that it's estimating. If that's not true, we have bias. And there are a few ways to get bias. There are a lot of ways to get bias, a few of which we have listed here. So one example at the top here is selection bias. And this is kind of, well, one of the things that we try to eliminate by taking that nice kind of random sampling. Selection bias might be something like if I'm measuring the average height of people in Pittsburgh and I choose to take my sample from, say, kindergarteners, or I go to a grade school and take a sample, or if I go to, you know, the basketball team practice or something from my high school and I, you know, sample people's height, there's probably a selection bias there, right? The group that I'm selecting for my sample is probably not representative of the population as a whole. Or another example of that might be like, okay, let's say I'm Gallup polls, I'm a pollster, I'm trying to call some people or trying to get an idea of how are people going to vote in, say, an upcoming election. Well, if I decide to call people on the phone using, say, phone numbers in the white pages, and I call at 2 p.m., I probably have a selection bias there, right? I'm probably going to get more, say, older folks, retirees, people like that, because they are more likely to have home phones that are listed in the white pages and to be home at 2 p.m. I'm probably not going to get very many younger folks who don't really have a home phone; they have a cell phone, and I'm probably not going to get many folks who are working because they're not going to be available at 2 p.m. On the other hand, if I used, say, a Twitter post or something like that, or X or whatever the heck it is these days, if I use the poll on there, well, now I've got a different problem, right? How many 70 or 80-year-olds, use Twitter or X, whatever you want to call it? Not very many. I'm going to be getting typically a younger demographic that's more tech savvy. So those would be examples of selection bias. So doing something like a random sample where I take everybody in the population, number each one of them uniquely, and then draw random numbers, and that's my sample. That would hopefully avoid something like selection bias. But in practice, of course, that's not the easiest thing to do. So confirmation bias is actually a really important idea. It's I would say a bigger idea than just what we're talking about here. But confirmation bias is the idea that if I have a point of view of the world, especially if I have one that I strongly adhere to, that I strongly hold, that I've invested a lot of time and energy and cognitive resources and so on in having that point of view and holding it and defending it, I'm going to tend to view information that comes in support of that very differently than information that comes in that refutes that idea. So that's kind of what confirmation bias is when I gather new data from the world, if it confirms my point of view of the world, I tend to view it favorably. I tend to be very open and accepting to that data. Whereas if very similar data with a similar level of reliability were to come in and refute what I believe about the world, I'm going to be much more skeptical just naturally of that data. I might write it off. I might say, oh, that person, they're just looking to whatever further their cause or something like that. So that's the idea of confirmation bias, that I don't treat each piece of information or each piece of data equally. And really, I would argue that the entire scientific method is an attempt to counteract this natural confirmation bias that we have. So roughly speaking, what is the idea of the scientific method? It's I establish a hypothesis, something that I think might be true about the world, and I try really, really hard to disprove my hypothesis. I don't try really, really hard to prove my hypothesis. I try really, really hard to disprove it. I come up with an experiment. I formulate a hypothesis that is refutable with empirical evidence. I come up with an experiment that could refute it empirically with experimental evidence. I run the experiments. I make sure try to think of everything I can think of where I could refute my hypothesis. And if I can't think of it, then I publish it and I let the scientific community do the same. I let them try to tear it apart. And if it withstands all of that and repetitions of people running experiments trying to tear it apart and nobody can tear it down, and if it withstands that test of time, then I maybe say, okay, this is kind of an established scientific theory or a scientific statement. So that's the idea of confirmation bias. Survivor bias is an interesting one. So one example here is the walled plain study. And let me bring up a picture here. So let's talk about this for for a second. Okay, so if you look at this diagram of a plane here with these red dots on it, the story that's behind this is from World War II, and there was a statistician, Abraham Wald, who now was kind of famous for doing this work, and he was working for the Royal Air Force, the British folks, and what they wanted to know, they're in World War II, right? The air battle is an important component. They want to know, okay, we have these planes, we want to put some more armor on our planes so that they're a little more resilient to getting shot down. But we can't turn a plane into a tank. You can't just put a whole bunch of armor everywhere. It won't be able to take off or won't be able to maneuver well in a firefight. So, right, we want to put a little more armor on, but we want to be very selective about where we put the armor. We'll put a little more armor on important parts of the plane and maybe leave the other parts of the plane so that it can still take off, it can still get good fuel efficiency, maneuverability, all that. So they ask Abraham Wald, can you tell us where we ought to put the armor? And so what Abraham did is he sat on the side of the runway, he watched the plane take off. It would go get into a firefight. He'd see the planes that come back from the firefight, he'd watch them land, and then he would, on a little piece of paper, he'd put a dot where he sees a bullet hole on that plane or a new bullet hole on that plane. And this is something, this is a representation of something like what he saw. And on the basis of this, he made a recommendation where to put the armor, where to put the extra armor. Any thoughts on where you might want to put the extra armor?
Is it on the dotted part?
Sorry?
On the red dotted part?
Yeah, so I think the natural answer is, well, let's put the armor where we see a lot of red dots. Where there are a lot of bullet holes, let's put the armor there, I think would be the natural, the natural inclination. Does anybody have a different thought?
Maybe because the places that already had bullet holes, but the plane already landed, so it means that it didn't kind of made too much problem. So maybe not that places, but the places that didn't have it.
Yeah, exactly. And this was Abraham Wald's big idea, was maybe not his idea, but he applied this idea of survivor bias. It's very important to note that these are planes that landed, which means they returned from the firefight, presumably, especially back in whatever 1940 or something. They're just randomly shooting at one another. We would expect that a plane just randomly getting shot at would have a pretty uniform distribution of bullet holes over the plane. So if I watch the ones that came back and landed, well, the plane that got hit on the edge of the wing out here, or maybe in the middle of the fuselage, it seemingly was able to make its way back and land. So that wasn't a devastating hit to that plane. But the planes that were hit in the engines, or the planes that were hit in the cockpit, or in the tail gunner area, or in these areas of the wings where they hold the fuel, that's a much more devastating hit. Those are probably the planes that crashed, presumably, and that we don't see coming back. We don't see those as survivors. So Wald recommended that where you don't see the bullet holes, that's probably where the plane got hit and crashed. Let's put the armor there to support those areas, because we can tolerate a hit in these areas. We see a lot of planes coming back with hits in the middle of the fuselage. We can tolerate a hit there and still, stay in the fight and come back and land, but maybe not to the engine or the cockpit. Let's put extra armor in those areas. So yeah. So that's an example of survivor bias. Another example of survivor bias, we have some folks who I think are interested in finance. If you look at hedge funds, so what a hedge fund is, it's kind of like a mutual fund. Most people know what mutual funds are. You kind of invest in them, maybe in your retirement portfolio. You give money to a company, and they kind of pool your money with a whole bunch of other people's money, and they buy a big collection of stocks. So that's what a mutual fund is. And mutual funds have to kind of give you a ton of information. They have to tell you exactly what kind of stocks or securities they're planning to buy, in what proportions. They have to tell you, roughly speaking, exactly what they're invested in, what their biggest holdings are, all of this kind of stuff. They have all kinds of disclosures. Hedge funds are fairly similar in theory, but they don't really have to disclose anything. So they can be much more secretive. And what they do is they come up with strategies that they think are going to do better than the rest of the market. So they hire Nobel laureate economists and people with PhDs in computational finance, all of these kind of folks. They have tons of supercomputers and very fast links to the Wall Street computers for trading and all of that. And they use all of these advantages, and they hope to get themselves an edge over the market. So they are very secretive. They don't really tell folks what they're investing in. And as a result, the average person is not allowed to invest in hedge funds because they can be very risky. So they can take big risks. If the risk pays off, you make a whole bunch of money. But if they take a big risk and it doesn't go so well, they can easily go bankrupt. One example of this is Long-Term Capital Management, a pretty famous hedge fund that went bankrupt. So the interesting thing with hedge funds is, if you say, okay, today, if I look at the hedge funds that are out there today, and I look at their performance over, let's say, the last 10 years, they look amazing. It's like, something like 25% return or something. You're like, wow, they just like blow the market out of the water. They do amazingly well. But here's the question, though, is of the hedge funds that are around today, we're selecting for the survivors. If you think hedge funds do risky things, they can, really succeed, or they can kind of crash and burn and maybe go bankrupt and maybe lose all of your money. So if I look at, a list of the hedge funds today and then rewind to 10 years and say, how did these ones that are still alive today do over the past 10 years? They might have look like they've done very well. But if I went back 10 years and I said, what are all of the funds that were there 10 years ago? I have these ones that were there 10 years ago, but aren't there today. And then I fast forward and say, how did these do as a collection? Well, the ones that crash and burned maybe don't make the whole collection look so hot anymore. So there's a survivor bias. If I look at the funds that are available today, still around, go back 10 years and say, how did they perform? I'm only looking at the survivors. And of course, if I was back here 10 years ago, and if I could choose one of the ones that's not going to go bankrupt, I could realize that very nice margin over the market. But picking which hedge fund is going to succeed versus go bankrupt is probably as hard as, or maybe even harder than, picking which stock is going to succeed or go bankrupt. So you can't really rely on being able to do that. So really, this is the perspective we have to take. I have to pick when to invest my money and then see what happens 10 years from now. I don't get to, see what happened today and then say, oh, I wanted to invest my money in this one 10 years ago. You can't do it that way. So there's a survivor bias in hedge funds as well. Estimator bias, I'm going to give kind of a silly example here for estimator bias, but estimator bias is where the sample statistic, we have a calculation for it. We have a mathematical expression that says you have your data, your raw data from the sample. This is how you compute this sample statistic. What if that mathematical expression simply is wrong in some sense? So let's say that I want to know the average height of people in Pittsburgh, and I say that my average height of my sample, I'll call it, let's call it like X tilde or something. And I say I'm going to add up the heights of my 100 people. I'm going to divide by 100, and then I'm going to subtract 15. Well, I think probably most of us recognize this as the average. But if I kind of like compute an average and then like randomly for some strange reason subtract 15, do you think that my sample average that I compute here, this X tilde number, do you think this is going to be a good estimate of the population average? Well, probably not, right? Because I did this goofy thing where I subtracted 15. If I didn't subtract 15, I would probably guess that maybe this would be a good estimate of the population average, and I would be correct. Now you might say this is silly, who would ever do that? Well, there are some nuanced statistics that are out there. The average is a pretty easy one to deal with. But when we want to know, say, how spread out is the data, we might be interested in computing the variance or the standard deviation. And it kind of turns out that we have a way to compute the population variance and the population standard deviation that you do it according to this expression, this mathematical expression. But if I use that same mathematical expression to compute my sample variance, I actually end up with a result that's kind of like this. I can't use the same mathematical expression for my sample variance as for my population variance. Or if I try to, then I end up with a biased result. I end up looking at a number and thinking that my population variance ought to be around a certain number, but really that's an underestimate if I don't make an appropriate correction. So this estimator bias, I mean, this is a silly example. Hopefully nobody would really do this. But there are some examples that are a little bit more complex where we do actually run into this problem. And if we did things kind of in an obvious way that seems like the right way, we would end up introducing bias. Detection bias. I actually saw this report. I just saw the headline, so but I saw this report that there was some, like, I think it was like a little frog or something, some like little animal that they thought was extinct, and they like found one somewhere, basically using genetics. They, as we walk around, we kind of shed cells and things like that, and as these animals go around, they shed cells, and they figured this little guy was extinct. But people, biologists and people go around and just like collect random DNA off the ground in forests and things and see what they find to see, what animals are in that area or something. And they found like evidence of this. I think it was some kind of frog or something like that. So detection bias is like, how easy is it for us to detect something that we're looking for? Right? If I'm interested in knowing like how many parrots I think are in this certain area, well, parrots are brightly colored and loud and so on, like they're probably easy to detect. If there's one in this area, I'm probably going to see it. But if I'm looking for some little like slug or snail or something, it's a lot harder for me to know if there's 1 or 10 or 0 in, say, a certain area. Another example where detection bias comes up quite a bit is things like crime, things where you're investigating something about humans where we actively don't want people to find out, right? So if you want to know how many people, committed tax fraud in the last year, well, if you go up to 1,000 people and say, hey, did you commit tax fraud in the last year? Well, not very many of them are going to say yes, right? So that would be a detection bias. The number that we measure is almost certainly going to be less than the actual number, if we had a perfect measuring device or measuring method. So that's a detection bias. Reporting bias is kind of an interesting one. It can kind of cut both ways. In something like medicine, for example, if we're investigating, maybe we think this is a pathway that's altered in this cancer and maybe can be targeted with a drug. If we investigate that pathway and it turns out that it isn't actually altered in that cancer, and we just spent $200,000 of research grant money to find out we're wrong, we're probably not going to be super interested in publishing that and telling everybody, hey, we just wasted 200 grand of research money. But if we did find out that that pathway was altered in this cancer, we'd happily publish that, right? And similarly, if we send our papers into journals, the journal is going to be much more likely to accept and publish the one that does show a really interesting finding about something being altered in some cancer versus one that just says it's not. So reporting bias, the positive results are going to be much more often reported in, say, medical literature than negative results. On the other hand, if you think of something like finance, if I have an investment strategy that really works great, if I happen to find something that really beats the market, well, if I publish it, if I let everybody know about it, then I lose my advantage, right? My advantage in the market is only relative to other people. And if I give them the same model or the same idea that I have, everybody has that idea, everybody tries to implement the idea, and then the idea can't be successfully implemented. So I really want to keep that secret. If I find a strategy to beat the market on average over a long period of time, that would seem to contradict what's known as the efficient market hypothesis, which effectively says you can't do that. But there's lots of studies supporting the efficient market hypothesis. But if hypothetically somebody found a refutation to the efficient market hypothesis saying that if you invest according to the strategy, you can make a ton of money, is that person incentivized to publish that, or are they incentivized to use it themselves or like sell it to a hedge fund? They're much more incentivized to use it themselves or sell it to a hedge fund. So this could, in theory, cut either way. Status quo bias, I would say, is pretty similar to something like confirmation bias. If there's a status quo, if there's a kind of a generally accepted viewpoint or way of doing things, we tend to be much more amenable to that than to changes. And then in medicine, there's this interesting idea called lead time bias. We might say something like, okay, over the last 10 years, maybe we're interested in knowing whether our treatment of a certain type of cancer has gotten better. So maybe we look at, 10 years ago, somebody was diagnosed with this cancer. On average, how long do they live from diagnosis? And then we look at today, and well, maybe not today, but you get the idea. So we look at today and say, on average, how long do they live? And we notice a substantial increase in years lived on average from time of diagnosis. And we might be tempted to conclude from that, oh, well, our treatment of cancer has gotten a lot better because people are living longer after diagnosis today than, say, 10 years ago or 20 years ago. But really, there's kind of two ends to that spectrum, right? We could have gotten better at treating cancer, extending the lifespan of the person, or we could have gotten better at detecting cancer. Maybe the person's life today isn't any longer than it hypothetically would have been 10 years ago, but we just detected it earlier. We had more lead time. We moved that starting point up when we started counting, time after detection. So that's something that kind of comes up in the medical literature, that over time we tend to get better at treating things and also get better at detecting things. And that kind of moves the end point, the age the person would have died at, it moves it back. But also it moves the start point, the age that the person knew that they had the disease, and moves it forward. So that's that lead time bias. If we're looking at, say, lifespan after diagnosis, we have to account for the two variables that could affect that, and not just presume that it's, say, a treatment effect. Okay, are there any questions on chapter 1? Chapter 1 was a pretty huge chapter, but it's a big introduction to just a ton of different concepts. Are there any questions on chapter 1? All right, so on to chapter 2. And I think I will keep the window here a little bit bigger because we'll be talking about graphs and things, and it would be nice to just have a little bigger of a window, and don't think I need to make as many notes. All right, chapter 2 on summarizing and graphing data. So now we're kind of digging a little more into each topic. So chapters 2 and 3, we're looking at descriptive techniques, descriptive statistics, taking a big data set and maybe crunching it down to, say, one number, say maybe an average, that'll be in chapter 3, or maybe taking this big data set and trying to turn it into a picture, something that's easier to digest than, say, looking at 2,500 numbers in the raw data. Having a picture might be easier for me to understand. And that's going to be the focus of chapter 2. So kind of a little side quote here. This is really more about chapter 1 as we enter into chapter 2 and wrap up chapter 1. This is from Sherlock Holmes. And in one of the Sherlock Holmes stories, he says, "It is a capital mistake to theorize before one has data. Insensibly, one begins to twist facts to suit theories instead of theories to suit facts." So any thoughts on this quote? Do you think this is a correct quote? Do you think it's incorrect? Do you think it's conditional? Any thoughts? So when I read this, I thought it was kind of interesting because I started thinking to myself, well, it's a mistake to theorize before one has data, but that seems to be in direct conflict with the scientific method, right? You hypothesize, you come up with an idea, you theorize, then you come up with an experiment that can refute your theory, and then you gather data to see if that refutation happens or not. So this seems to just blow the scientific method out of the water. I think the interesting thing here, though, is that Sherlock Holmes is a detective. So he's showing up, almost always after the crime has been committed. He's got a static crime scene. The murderer, the whatever, has already left. So what type of experiment, so to speak, is he typically conducting? Well, he's typically conducting an observational experiment. He's typically going in and just saying, okay, I have this room where the crime occurred. Let me observe. Let me see if there's anything that I notice that I think is out of the ordinary or interesting. So in his case, in an observational experiment, maybe theorizing first is going to bias his collection of the data. Maybe if he says, oh, I think I know that, I think I already know what happened. I think this happened. Maybe there will be a piece of information that he overlooks because he says, oh, that's inconsequential because I already know what happened. Or a piece of information that he overweights because it's in line with what he thinks has happened. So maybe in an observational type of study, maybe you want to be a little hesitant about theorizing too much. But in an experimental study where we're really trying to apply the scientific method, theorizing first, and then being very careful to come up with an experiment that is capable of refuting our hypothesis and trying really hard to refute our hypothesis, and then going out to the greater scientific community and letting them all try really hard to refute our hypothesis. Maybe that's why we need such rigor in something like the scientific method or in science in general, because we ought to be really careful that we don't twist the facts to suit the theories. Okay, so if our end goal here is to generate a graph, an intermediate goal would be to just take our raw data that's kind of this huge, just messy, unorganized data, and maybe first organize it. So we like to organize the data. In this case, we'll organize into tables. And then from that table, we'll try to construct graphs. So the first little bit of this chapter 2 is organizing data into tables. And often we want to create frequency distributions. So again, raw data is data in its original form. It's as we collected it. If we're looking at a sample of heights of people in Pittsburgh, it's just like, 5'9", 5'7", 6'2", just a list of all of that data. A frequency distribution, we organize that raw data in a table, and we use something called classes and frequencies. So classes would be kind of the names of the bins that we're sorting the data into. So maybe, people between 5'2" and 5'4", people between 5'5" and 5'7". Maybe I set up bins like that. And then frequencies, they're the counts of the number of raw data points that fall into that bin. So let's look at an example. Say we have a food survey and we ask some people, which drink do you prefer, A, B, C, D, E? And this is our data. This is our raw data. We have a 5x5 grid of responses. So our first respondent said D, Dr. Pepper. Our second respondent said A, third said E, and so on. So we just have this list of 25 letters. Really hard to glean much information from this. And certainly if we had 2,500 people, be very difficult to really say anything about this data set. But what I could do is I could set up classes or bins, as I tend to call them. I could say, okay, what are the different responses? A, B, C, D, E. I could create a class for response A class for response B, C, D, E. And then I could evaluate the raw data and find a frequency. So the frequency for class A is the number of data points that have value that falls into this bin or that have value of A. So if I count here, I have 1, 2, 3, 4, 5, 6, 7 A's. So the frequency for the class A or for bin A would be 7. There would be 4 B's, 5 C's, 3 D's, 6 E's. So class, or what I'll often call bin, just like a bin, like a little box that you use to collect something. That's the categories that we're using. And then frequency is the number of data points. If I imagine just kind of having these bins sitting out on my table and I like physically were to pick up each of the data points and look at its value and then toss it into the appropriate bin. How many data points end up in bin A? Well, that's 7, 4 for bin B, and so on. My classes or my bins should be constructed in such a way that they're mutually exclusive and exhaustive. In other words, what I mean by that is there should be no theoretically possible data point that could not fall into a bin. So for instance, if I had a choice F here for, I don't know, what's a different soda, say Coke. If I had F, Coke, I wouldn't want to have classes just A, B, C, D, E, because somebody could have responded F and then I missed them. That would not be an exhaustive list. That wouldn't be an exhaustive set of classes. They should also be mutually exclusive. I shouldn't have overlaps between bins. I shouldn't be able to put one data point into 2 separate bins. So I shouldn't have like the first class be like A or B and the second be B or C, because somebody that answered B kind of ends up getting put into both bins. I want to count each data point exactly one time. I don't want to overcount it. I don't want to undercount it. I can add up my frequencies, 7, 4, 5, 3, 6. They should add to the size of the data set. 5 by 5 grid gives me 25 data points. And I see indeed that my frequencies add to 25. That's a nice check to make sure that I counted each data point exactly one time. Now, of course, I could have made 2 mistakes. I could have, overcounted in A and then undercounted in D, and maybe that offsets, but this is at least, one method of checking. So my total frequency should be the size of the data set. I could also talk about a percent in each bin. What percent of the data points ended up in bin A or bin D? And sometimes we call this a relative frequency, or quite often we call this a relative frequency. How do I get that? Well, 7 divided by 25, my frequency for the class divided by the size of the data set, or the total frequency, we can multiply by 4 over 4. We see we get 100 on the bottom. 28 over 100 is 28%. Right, so I can do 7 over 25 would be 0.28. I can do that on a calculator, bump the decimal point 2 places to the right, and make it a percent. So 28% of my respondents answered A, 12% of my respondents answered D, and so on. Sometimes we're in a situation like this where we have, say, grade data for an exam, and it kind of looks like the grading structure for the exam is from 0 to 100 in half-point increments. So I might say to myself, well, I suppose I could set up a categorical frequency distribution. I suppose I could make a list of all of the possible exam scores. I can make a list of these 201 possible exam scores and the frequency in each of them. But what's my frequency going to look like? It's going to be like 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0. Maybe I get a 2 somewhere. This is much, much worse to interpret than even the raw data. I just have a whole bunch of zeros and an occasional 1 and maybe a very occasional 2 or something. When my number of bins that I might naturally end up with is like way larger than the data, the number of data that I have, I probably don't want to go this route. I probably don't want to enumerate every possible outcome. So what's a reasonable thing to do? Well, a reasonable thing might be to group a bunch of outcomes together into a single bin, right? Maybe I say like 80 to 90, 90 to 100, and then anybody who scores like between 90 and 100 gets into this top bin. Anybody that scores between 80 and 90 gets into this second bin. So I take something that might be a little bit more like a continuous quantitative variable, or I'm kind of treating this like a continuous quantitative variable. And I'm going along that number line, and here's my number line from 0 to 100, and inserting breakpoints. So this is a bin, this is a bin, this is a bin, right? I'm grouping together a lot of outcomes into a single bin. And again, this comes with a trade-off. The downside is that I kind of lose nuance, I lose detail. If I just tell you that there were 10 people that scored between 90 and 100, you don't know whether that's like they were all 91 or they were all 99 or they were kind of spread out. So we lose some detail, but we gain some insight, hopefully. I do have to be a little careful because I want to maintain that idea of mutually exclusive and exhaustive. I want each possible data point or each possible data value to be in one and only one bin. So I don't want to go 80 to 90, 90 to 100, because then what do I do with 90? Or I probably don't want to go like 80 to 89, 90 to 100, because then what do I do with 89 and a half? It seems like 89 and a half would be a valid data value. So I might go something like this, 80 to 89.5, then 90 to 100. There's no data value between 89.5 and 90, at least seemingly so. Or if this was really a continuous variable, we might go closed 80 to open 89.5. So anything right up to 89.5, but not including 89.5, gets in this bin, and then closed 89.5 to 100 or something. Or I might actually put 90 here in this case. So coming up with these bins is a little bit of, it's as much of an art as a science, I would say. Typically, we want to choose bins that are equal sized. So, I have 10 points here, 10 points here, and so on. And I probably want somewhere in the ballpark of maybe 5 to 10 bins is usually pretty good. Maybe up to 15 bins is kind of acceptable. If I get over 15 bins, it really becomes just hard to look at, hard to understand. I just have so many bins that I'm working my way back towards having too much information for me to, or too much data on the page for me to interpret. So I would say, typically I'm going to shoot for something like 5 to 10 bins and roughly equally sized bins. Now, the one exception to that kind of equal size is what we might call a catch-all bin. If I look at my data here, I mean, I guess I could do like 0 to 9.5, 10 to 19.5, 20 to 29.5, but I see that the frequencies for all of these lower value bins are all going to be 0. That can just be kind of annoying to look at, to include all of these lines that just have 0 frequency, or when I make a graphical representation of this, to have like a huge chunk of the graph that's just like completely blank. So I might choose to make a bin that's something like, less than 60, and then like 60 to 79.5, and so on. I might use this as kind of a catch-all bin because I see that there are, a couple of scores that are less than 60, but very few that are over there. So I might make a catch-all bin so that way I don't just have a whole bunch of bins or a whole bunch of classes with zero frequency. That's something that's done quite often. And we'll see that we do that here. So my boundaries, let's say I set as 89.5 to 100, 79.5 to 89, 69.5 to 79, 59.5 to 69, and then 0 to 59. So each of these is approximately 10 units wide, with the exception of the catch-all bin, which is much wider. And I see that my frequencies, I have 9 data points that have a value from 89.5 to 100, including those endpoints. I have 5 data points that have a value from 79.5 to 89, including the endpoints, and so on. And again, if I know that my data are in increments of 0.5, then I'm never going to miss a data point. I'm never going to have a data point with a value, say like 89.3, where it kind of falls between these first two. And also I know that these bins don't overlap. So I'm never going to have a data point with a value that is in 2 bins simultaneously. So I shouldn't undercount or overcount my data. And again, if I add my frequencies up, I get 25, and I can verify this is a 5x5 grid. There are 25 raw data points, and I've counted 25 data points. That's some confirmation that I've done it correctly. Are there any questions on anything so far? I do see some in the chat. When I have my screen in full screen view, I typically don't have chat up because it has to be over some page. So yeah, let me just take a look back through chat. Yeah, so the discussion of bias in AI is a really interesting one. So just going back to something that was asked in chat. It's a very interesting one. There's a lot that can maybe be said about it. There's probably a lot that can be said about it that I don't know. But one great example is, for instance, AI models maybe are trained on, let's say, historical works of literature, right? Well, historical works of literature, what do you mean by that? Well, in America, we typically mean literature that, is Western literature, primarily maybe written by men, that kind of a thing. So there might be some biases like that that are fundamental to the AI system, right? If we train a model we have to train a model on a certain data set. If we train a model on a certain data set, and then we claim that the model can make predictions if we claim the model can make predictions about a system that is not that data set is not reasonably representative of, then we have a problem, right? If I say I'm training a model on Shakespeare's works, and this model is going to talk to you as if it were Shakespeare, that model probably does what it's supposed to do. If I say I'm going to train a model on Shakespeare's works, and this model should, be able to talk to you in as if it were, any author that you want, or from anywhere in the world, from any point in time, that model is probably not doing what it says it's doing. So that's an important note, is we always have to be cognizant of assumptions. And one of the, math, we have assumptions. We say we can apply the result of this theorem if these explicitly stated assumptions are true. In AI, kind of an assumption in a sense is that the system we're interested in knowing about or studying with the AI is reasonably represented by the data that the AI was trained on. So that's an implicit assumption. And I don't know the extent to which that's true for, say, a typical AI model, but that is an excellent question. And that's a big part of AI ethics these days. So Yeah, that was a really good question from Tyler. Yeah. Okay. Yeah, when if you ever post something in chat and I don't address it, just you can just unmute yourself and ask too, or make the point. Especially when I'm in full screen like this, I usually don't have chat open. Okay. So any questions on anything that we are talking about here? All right. So now we have an idea called a cumulative frequency distribution. And you'll notice it looks pretty similar to the previous ones. We have certain class ranges and certain frequencies for those ranges, but these bins are not mutually exclusive, right? My bins, instead of looking like this, what my bins actually look like is this. There's the first bin, here's the second bin, here's the third bin, here's the fourth bin, and so on. So we're intentionally double and triple and quadruple counting data values in a sense. So the idea over here is we might think of this first class as being like, the Fs, how many people failed the class, or failed the course. We might think of the second class, 0 to 69, as like the Ds or Fs. And then the Cs, Ds, or Fs. The Bs, Cs, Ds, or Fs. And then the last class should be everybody. So the cumulative frequency, we have, say, some folks here, and we have some folks there, and some folks here. We're accumulating more data points as we go along. So in this first bin, we just have these 3 blue ones. In the second bin, we have the 3 blues, say, plus the 2 greens. These aren't the same numbers as over here. In the third bin, we have our 3 blues, our 2 greens, and our 5 reds, right? So that's how we get a cumulative frequency distribution. So our cumulative frequencies would look like 3, and then 3 plus 2, 5, 3 plus 2 plus 5, 10, and so on. So our cumulative frequency is an increasing function, maybe more technically a non-decreasing function, but it only either goes up or stays the same from one line to the next. Because we're just, making our bin bigger and bigger, it's going to, collect the same number of data points or perhaps more, but it's never going to collect fewer data points when we make it bigger. Okay, and then lastly, we can imagine a scenario where we have numerical data, we have quantitative data, but maybe we don't have like 200 possible outcomes like we had here. Maybe we just have a few possible numerical outcomes. So here, for instance, if we have a satisfaction rating, we send our customers a survey and we say, how happy are you with service? 1 to 5 stars. We've already talked a little bit about the 1 to 5 issue. Maybe 0 to 4 would be a little better, but we'll leave that aside for now. And these are the responses. I might be tempted to say, oh, this is quantitative data. I probably should just group it, but do I really need to group it? Or can I even realistically group it? What are my groups going to be? What are my classes going to be, like 1 to 3 and then 4 and 5? Like, that doesn't really get me anywhere. That's too few classes if I tried to group this together in any way. And the grouping, the groupings, the classes would be of unequal size. We can just leave this ungrouped. We can pretty much just treat this like categorical data, like a categorical frequency distribution, and just list each possible response, 1, 2, 3, 4, 5, along with the number or the frequency, and then the percent if we want. Now, there is one caveat here. If we were listing, our drink preferences, Pepsi, Dr. Pepper, whatever, it doesn't much matter what order we list them in. Because remember, categorical data, it essentially has no structure. It doesn't even have ordering, a natural ordering to it. But for an ungrouped frequency distribution, where we have quantitative data, we should respect that with quantitative data, we're going to have an ordering. There's a natural ordering. 5 stars is more than 4 stars, is more than 3 stars, right? And a 5-star rating is like a better rating. We did a better job for that customer than a 4-star, and we did a better job for them than the 3-star. There's a natural ordering or ranking here, and I should respect that in my classes. I don't want to, go like in my classes 1, 3, 5, 4, 2 or something. That would be kind of goofy. I want to respect that ordering. So I either want to go 1, 2, 3, 4, 5, or perhaps 5, 4, 3, 2, 1. But I want to respect that natural ordering or ranking in something like this, where maybe with a categorical distribution, there's less importance to that. Okay, any questions on the organization of data into tables? All right, so from this point forward, we're going to presume that we have taken our raw data, a big mess of just a big collection of data, and that we've organized it into a table. And a table is, it's a step in the right direction. This is easier to understand and to glean some knowledge from than this is. But a picture is sometimes worth 1,000 words, or is worth 10 lines of a table. So let's look at pictures, graphical representations of data. Not only do these maybe look a little more appealing than just numbers on a page, but these often can be easier for us to read too. They can be excellent. They can be excellent descriptive techniques. So a histogram or a bar graph or a bar chart or a column chart, there's lots of similar names for what's effectively the same representation. It looks like this. I think all of us have seen this type of descriptive technique before. And the idea here is we use a bar graph to visually represent the frequencies of the classes. So we have, again, our grade data from over here, where we grouped the different outcomes into 5 classes, one of which was a catch-all, the 0 to 59, and then the other 4 had width of about 10 units. For my bar graph, what I do is I start by writing out across the bottom, across the horizontal axis, what the different classes are. So I had a class 0 to 59, a class 59.5 to 69, and so on. And then for each of those classes, I look at what is the frequency. So the 0 to 59, there were 5 instances there. So I make a bar of a certain width that is at height 5. Note that on my vertical axis, I'm starting at 0, then 1, 2, 3, and so on. So I go to height 5 with a certain width. Each of my bars should be the same width, and then the height will vary according to the frequency. Now, something that we note is that for 59.5 to 69, that was one of the classes, but we had no data points that had a value in that bin. That's fine. We leave that there, but we just don't write a bar. So it's important that we leave this here and we just have the space. There's just not a bar for that one. There was no data in that, no data point with a value in that interval. For our C's, our 69.5 to 79, we see again, we have a bar above there with the same width as the first one, but at height 6, because we had 6 data points that had a value in the 69.5 to 79 range, and so on. So this is how we would go through and create a histogram. We could do this by hand. We could do it on Excel. And after we finish this PowerPoint, then we'll switch over to Excel. That'll be next time. We'll switch over to Excel and we'll look at how to construct some of these graphs on Excel, have it do some of the legwork for us. Another example of a histogram is the survey response data, 1, 2, 3, 4, 5. How did we perform? We got 1, 1, 3 2s, 2 3s, 6 4s, and 4 5s. You notice that there is a little bit of a difference in the visuals here. These bars are wide enough that they touch one another. These bars are a little skinnier. Again, I think this has to do with some of those nuanced words where do you call it a column chart or a histogram, but we're basically going to use those as interchangeable. And there are tons of little details you can change like this in Excel. You can make the bars skinnier or wider. You can make them different colors. You can have an outline, on the border, all kinds of different things you can do to kind of tweak the visuals to look, a little more interesting. So here's a little bit of a joke bar graph. So here we would have categorical data, the different file extensions, and somebody's assessment of the trustworthiness of information by file extension. If it's formatted in TeX, which is basically a mathematical typesetting language, it's probably very reliable. If somebody knows how to write in TeX, they're probably not going to write things that are wrong. PDF maybe a little less than that, but still pretty good. And when you get down to like, if your information is being conveyed as a picture, maybe a little bit less reliable. So I like these XKCD comics. They have a lot of good comics. Here's an example that I really like for that's related to this idea of histograms. So what this is for each state, and let me go to the next slide so we can zoom in a little bit and see a little better if you're on a small device. For each state, for each of 10 years, these histograms, these bar charts basically represent the change, the percent change in population for each year. So we can see, for instance, Pennsylvania just kind of had a nice slow and steady increase over these 10 years. We can see Rhode Island had kind of a couple years where they were increasing and then several years of, substantial decrease. And we can see, say, somewhere like DC, where it had, a negative year or so, but then several years in a row of really strong increase. The other nice thing here is the color coding. Going from yellow to deep red is a greater increase, and then the blues are the decreases. I actually just really liked this representation because I thought you think about this, 50 states plus DC, so 51 locations, 10 years each. This was 510 pieces of data. And really at a quick glance, we can actually tell a lot. We can pick out a couple of really interesting features that if you just gave me a grid of, say width 10 and height 51, it would probably be a much more difficult task for me to tease out something interesting from that. So can anybody point out something interesting that they see? I think there's a few things we can glean from here. Anything interesting that pops out?
Is that Hurricane Katrina in New Orleans?
Yeah, that's kind of the big like sore thumb or something, is what the heck happened here? Why was there such a huge 1 year decrease in population? Exactly, that was Hurricane Katrina. We saw all these people move out of the New Orleans area looking for housing somewhere. We actually see in that same year, Texas got a bit of a bump. Georgia got a bit of a bump. Florida, these two down here, Mississippi and Alabama, right? So we see a lot of, in Missouri even a little bit, we see the surrounding states get a bump that same year as people kind of, moved out of the area, looked for different options, and then it seems like they had a few years of positive growth as people kind of rebuilt and started to move back. Anything else that we see that might be interesting or noteworthy, or
people moving to a warmer climate, but then like kind of, or maybe it could be a spike in tourism population as well.
Yeah. So if we look at generally the bottom half has a lot more red, and the top half of the map, the northern half, has a lot more blue, right? So not a ton of blue, but still, like, we don't see nearly as much red up. And the northern climates, we see, the Southwest seemingly had a pretty significant boom. Texas, 10 years in a row of pretty strong growth. Georgia and Florida, generally pretty strong growth. Same with the Carolinas. Yeah, people moving to warmer climates. Maybe as the boomers start to kind of age and retire and look at moving south. We see, I actually found it interesting that like Alaska has really good growth. I mean, not somewhere that I would have thought that people would be moving to, but so that's kind of interesting. And Hawaii also seems to have good growth, but I think that's, you know, pretty self-explanatory. Who wouldn't want to live in Hawaii, especially in January or February in this climate? But yeah, so we can at a glance look at 510 pieces of data, and the combination of the bar charts, the nice use of the visual representation, splitting them up on the US map, and also the coloring, the darker reds, the blues, all of that kind of combines to make a very nice graphic where you can look at a glance and pick out a few interesting things, or you could look a little more detailed and you could say, hey, I'm really interested in Pennsylvania, what happened here? And also tell very quickly, oh, okay, slow and steady growth. Okay, you know, or I'm really interested in what is this up here? This one with a couple of blue years. It's escaping me. I want to say Maryland, but I know Maryland's not here. But anyway,
Massachusetts.
Yeah, Massachusetts. Yeah, I had the M. I was like Maryland. I guess it's the Ravens that are in my head or something. I don't know. Yeah, Massachusetts with the like why were there a couple years that they went down in population and then they seem to have recovered? Maybe if I was, you know, in Boston, I might be interested in thinking, wait, why is that true? You know, the data might lead me somewhere. That might lead me to ask some questions and then try to go further and answer them. Or I could have questions that are answered by this data. So by doing exploratory data analysis, which would be like, hey, I collected a bunch of data, let me just plop it down on a nice visual display and kind of explore it. Let me just look at it and see if there's anything interesting that I see that might lead me to ask questions. Or I might have a question in mind, and collecting the data and analyzing it might help to answer some of those questions. So it can go either direction. Here's another example for the folks interested in science and medicine and so on. GCMS results, so gas chromatography, mass spectrometry. Basically, this is a big machine, and you put a chemical in one side or a, you know, a sample with a bunch of chemicals in, and it basically sorts the chemicals by something like size and then something like mass to charge ratio. So it's a big machine. It's kind of complicated how it works, but it gives you a printout like this, and it has these little spikes, these little kind of like histograms. So this is going to be a grouped frequency distribution. Basically, this is some kind of intensity, and this is mass to charge ratio across the bottom here, and it's going to group together into a certain bin, maybe of size 1 or 2 or something. All of the data that has that mass to charge ratio, and then it's going to give you an intensity or something like a frequency going along with that. It's going to give you this chart, and then then the computer will take this chart and it will compare it to a library of known chemicals that have, you know, that were purified, run through a GCMS, and had their charts, you know, figured out or computed. So there's a library of all these known charts, and we have the chart for the thing for our sample, and we compare that chart to the known charts, and we see which one it matches up best with. And in this case, it's some kind of alcohol kind of deal over here. So I forget what chemical that is off the top of my head. Or we could represent that information like this instead. So similar information from a GCMS. This is slightly different. This is retention time instead of mass to charge ratio. There's a slight difference there, but we could represent it like this instead, with more of a line chart than a bar chart. And we'll talk about line charts in a little bit. But for some data types, you have a choice. You could use this kind of representation like a histogram, or a slightly different representation like this one here. So a so-called frequency polygon, I don't know why the book uses these crazy terms, but a frequency polygon is just what everybody else calls a line chart or a line graph. What's the idea here? If I chose to represent my GCMS results instead of like with these bars, these kind of discrete bars that have this very discrete feel to them, where like one bar seems to be unrelated to the bar adjacent to it. That makes sense in something like this, for instance. If I'm looking at grade data for a class, is the number of D's kind of like seemingly inherently tied to the number of C's? Probably not. But maybe if I'm looking at this, if I look at intensity at one time and I look at intensity a millisecond later and a millisecond after that, I might expect that those intensities are kind of related to one another. That if I see a high intensity at one point in time, I'm probably also going to see a relatively high intensity a tiny bit of time after that or a tiny bit of time before that. Or if I was looking at a stock price, I might think that the price today is probably going to be pretty close to what it was yesterday, and the price tomorrow is probably going to be pretty close to what it was today. If I want to really try to convey that tying together of adjacent data points, I might use a line graph or a line chart instead of something like a histogram. Now, in this case, I could make a line chart for my grade data. I can, do it. I can plug the data into Excel and make the chart, and that's fine. What is a line chart? Well, instead of the heights on the y-axis being bars, they're just points, and then I just connect the dots. So I make a point above 0 to 59 at height 5. I make a point above this 59.5 to 69 index at 0, and so on, and then I just connect the dots going across. But is this really a good graphical technique for something like grade data? Probably not, because this is going to kind of lead the viewer to kind of tie together adjacent data points. And for something like grade data, numbers of A, B, C, D, F, maybe that's not something that I want somebody to naturally be led to do. But would this be good for, say, stock market data? Yeah, probably. If this was like day-to-day closing price for a stock or something, this would be a great thing to do, because I do want the person to think that, relatively close together data points are, their values are inherently related. So again, the descriptive technique we choose can relate to what type of data we have, whether it's qualitative or quantitative, whether it's discrete or continuous. It can also relate to what we want to communicate or what we want to be in the front of the person's mind when they view this picture. So I might not go with a line chart here for this grade data, but a line chart might be great for something like this. Again, in the kind of scientific field and medicine, this is the output of a Sanger sequencer, so a genetic sequencer. And again, this is measuring something like intensity of fluorescence for 4 different colors, each color being related to one of the nucleotides, one of the genetic bases. So we see up top here, the computer's making these calls. So we have, adenosine and cytosine and guanine and so on going across here. And that's related to these intensity spikes, the spikes of the intensity of the fluorescence of the chemical as it passes by a sensor. So this is the readout of somebody's genetic sequence for some gene at some location. So just zooming in case somebody's on a small device, you can see it a little better. Or this is what a kind of full page readout might look like. So we do see a little bit at the very beginning up here, say on the top left, where it says N, and you might see that there's kind of like a few different spikes of about equal height there. And that's an area that the computer really can't make the call. It doesn't feel confident predicting one over the other. And that, as a side note, that tends to happen with Sanger sequencing, is it takes, a few bases or really a few dozen bases to kind of get started to where it's pretty reliable. And then it goes and it's pretty reliable to maybe, somewhere in the ballpark of a couple hundred bases long, maybe 300, 400 bases, maybe even a little bit longer than that, depending on how good the lab is, I suppose, depending on the impurity of the sample and how good the chemistry was done and so on. So again, this might be a great example for a line chart, because over time, we would expect that intensities, say kind of something like how much cytosine signal we're seeing this time versus a millisecond from now versus 2 milliseconds from now, I'd expect to kind of be closely related to one another. So a line graph might be a good choice here, because I expect those adjacent data points to be pretty closely related. And again, a word that I had never heard before teaching this course, an ogive, but really what we would just call a cumulative frequency chart. This is a chart of cumulative frequencies. We typically use a line graph for this because with cumulative frequencies, when we're moving from one bin to a bigger bin to a bigger bin, these are obviously pretty directly tied together, right? This bin is pretty inherently linked to its neighbors. So maybe connecting them with a line gives a little more of that sense of adjacent data points being fundamentally kind of linked together. Okay, so we've discussed this idea already, but relative frequency graphs, while we could have different classes with frequencies, and I can make my, say, histogram, for instance, like this, where my vertical axis is displaying frequencies, displaying number of each of the data points that are in each bin. Or instead, I could use the percents, right? I could use my relative frequencies. You see that the picture going back and forth essentially looks the same. Really, the only difference is what my index is over here on the left. Am I using the actual numbers of data points observed, or am I using relative numbers? Am I using percent in each of the bins? There are some advantages versus disadvantages. The advantages of using percents is if we have different data sets of different sizes, we can compare them on the same scale. So if I have my preferred beverage, and if I took a sample of size 100 in Pittsburgh and 1,000 in Cleveland, it might be hard to tease out, like, okay, 40 people like Pepsi and most in Pittsburgh, and 370 liked Pepsi the most in Cleveland, and it might be hard to compare those two numbers. But if I use relative frequencies, 37% versus 40%, moves everything to the same scale. So I think the other advantage is that scaling everything to a number between 0 and 100, I think is more intuitive for people to understand, especially if we have really big data like 10,000, 100,000, a million data points. We're just not used to looking at numbers like 250,000, right? It's like, okay, how big of a difference is it from 250,000 to 280,000? Like, is that like 30,000 seems like a big difference, but on a scale of a million, maybe it's not so big of a difference. But if everything is scaled from 0 to 100, we're used to dealing with numbers in that range all the time. And I think we just have a much more intuitive understanding for that, right? So something like, what's 25% versus 28%? Is that a big difference or not? Right? That's much easier for us to interpret without having to think too much about it. If I present a piece of data or a description to somebody, and they have to stop and think really hard about it to understand it, that kind of has taken away from the benefit of that descriptive technique. So it's not just the question of accurately representing the data, it's also a question of how's a person going to interpret this? Can they look at this and interpret it quickly and accurately? Are they going to be misled? Or is their natural tendency going to lead them to draw a wrong conclusion from what I'm presenting? Some disadvantages if I present a relative frequency, 0% to 100%, well, what was the population size, right? The famous like 4 out of 5 dentists prefer Sensodyne. It's like, okay, did you literally sample 5 dentists and 4 of them said they prefer Sensodyne, or is this like 5,000 dentists and about 4,000 of them prefer Sensodyne? And also sometimes we care a lot about scales, like if we care about, you know, not just what your percent, the percent of your, you know, say a certain car salesman's sales were on Monday, Tuesday, Wednesday, Thursday, Friday, but we might actually care a lot about how much they actually sold. You know, how many dollars total did you sell? That might be very important. So sometimes scales matter. Okay, any questions up to this point? All right, so the next topic that we're going to get into is distribution shapes. And we have 5 distribution shapes. I think this is going to take us more than the 7 or so minutes that we have left in class. So we're going to end class here unless there are any questions, and we'll pick up with this slide next time. And we should finish up the chapter 2 PowerPoint next time and probably get started into the Excel material. Maybe the Excel material will bleed over into the next class. Are there any questions before we stop for today?